and some of the plans for 2015. If you're new to the WebEx format, hopefully you're able to see my screen by now. I'll share up my presentation. You've joined the audio conference, so hopefully you're able to hear me through the phone or through your computer audio. I have the microphones muted to prevent audio feedback. If you're having any technical issues, please use the chat option as we go along. I'll do my best to accommodate any problems you're having, but I can't make any guarantees. Otherwise, if possible, please leave your questions or comments to the end. I'll do my best to allow 5 or 10 minutes for a question and answer session. If there's something that comes to mind afterwards, please feel free to email me. My address is shown up on the screen there, and I can let you know what things we're working on if you have any other suggestions afterwards. And as I mentioned, we'll be recording the session so you can download it, share it with your colleagues at a later date. That should be available on our blog probably later this week or early next week. The outline for the session today, which should last about an hour, is to recap some of the new features which were added in the last release in version 2014.2, give you an idea of some of the plans that we're currently working on for the next releases. We're planning to have 2 releases in 2015, and also some of the developments that we've been doing to support MODFLOW-USG. First, to recap the items that we added in the release in 2014.2, the focus or theme for that release was to address some pre- and post-processing options that were missing from Flex that were currently only available in VMod Classic. Along with that, we wanted to improve the user experience for colors, add support for some missing package and visualization options. So really with this release, you should be able to do more in Flex without having to pass your model back to VMod Classic in order to fill in some of the gaps. So we've improved the options for ZoneBudget, adding and removing particles for MODPATH. We've added support for the HFB, or horizontal flow barrier package, also called the wall boundary. You can now calculate and display the water table in a plan cross-section in 3D view. We've offered more flexibility for adjusting the colors and the legends when you're looking at properties and calculated heads or concentrations. And we've improved the colors for property and recharge zones, and also added a way to allow you to edit numerical model data in a CSV file. So let's go into a little bit more of each of those options in the next slide. The first one is ZoneBudget zones. So now you can create new zones for ZoneBudget using the assign, polyline, polygon, or single graphical tools. These are similar to what are available in VMod Classic. In addition, you can use any 2D or 3D data object that you've imported that satisfies point, polyline, or polygon geometry. So if you imported shape files and you want to use those for selecting ZoneBudget cells, you can do that. The nice thing is these can be either 2D or 3D. So if you have a 3D shape and it spans through multiple layers, that will select the appropriate cells for you. The other nice feature we've added when you create new ZoneBudget zones is you can have those span over multiple layers. So you'll see this option on the right-hand side. When you define your ZoneBudget zonation, you can select that to be calculated for the current layer or have that span over multiple layers. So this means you don't need to copy zones down to additional layers after creating the zones as you would have had to do in VMod Classic. In addition, you can create and edit the zone indexes for each cell via a CSV file. So if you've got some scripts or other means to define those ZoneBudget zones outside of the interface, you can do that by exporting the zone definitions out to a CSV file, define the zone index for each of the cells that you want over multiple layers, and then load that back in. So we really made it flexible for you to find the ZoneBudget zones that span over multiple layers. No need to copy those down to additional layers again. And the CSV editing really gives you access to doing an unlimited number of options. The next thing we've improved on is the ability to define particles for MODPATH. So previously you could only use a point data object. Now we've added more options for defining particles with the click of a mouse by using assign single or assign circle around a pumping well if you're doing a wellhead capture zone. Similar to what I showed you in the last slide for ZoneBudget zones, when you create particles, you can have those spanning over multiple layers, which means you don't have to create the particles for one layer and then copy them down to multiple layers later on. You do this all in one shot, which again makes it much easier to create those particles spanning multiple layers. We've offered several options for deleting particles. You can digitize a window or polygon around the particles you want to delete, and they'll be removed. This can be in the current layer. For example, you can delete all the particles in a specific layer, or delete all particles in all layers. These options are supported on MODFLOW 2000, 2005. We don't yet support particle tracking for MODFLOW-USG. I'll get to some of the ongoing developments we're doing with that afterwards. And we also don't support the MODPATH LGR version, which is designed to work with MODFLOW LGR. So again, we've really made it easy for you to assign particles spanning over multiple layers with a single mouse click. And there's flexible delete options allow you to quickly delete particles either in individual layers or globally. Next, we've added support for the HFB package, also called the wall boundary. This is typically used for modeling faults, either permeable or conductive faults. It can also be used if you're doing transport models where you want to set up a interceptor trench or a slurry wall in order to set up a pump and treat system. Similar to the other boundary conditions in MODFLEX, the wall boundary is defined with conceptual shapes. So you use a polyline to define the spatial extents, and you use the horizons to define the vertical extents of the wall. The attributes for the wall can be defined in a CSV file, which again makes it easy to adjust certain parameters outside the interface and load those back in. The wall features can be visualized in 2D and 3D views, and for 2D you can show this along a plan or cross sections, and I believe the next slide will illustrate that. The wall boundary is currently supported on MODFLOW 2000, 2005 for deformed grids. The key benefit with the way we handle the wall in MODFLEX over VMod Classic and other interfaces is that the cell faces are automatically calculated for you when you do the conversion of the conceptual shape to the numerical model. So those of you that have worked with this, if you know you've got anything other than a simple line going along a specific plane, it can be quite tedious to define which cell faces you want that wall to be applied to, whether it's the top, bottom, for example, the top and left side, or the top and right side. So we have a very sophisticated algorithm that'll do this automatically for you during the conversion. So it can be a really significant time saver. The other key benefits is that you can have these walls spanning multiple layers with very sophisticated line geometry, either a line that you've imported from a shape file or a DXF file, or one that you've just drawn within the interface. And similar to the options for ZoneBudget, you can do edits of the numerical wall parameters using a CSV format in Excel or text editors. Here are some examples of what the wall objects look like in MODFLEX. The conceptual representation is in the left side, where essentially you have a set of vertical planes that define the object in 3D space with a set of lines and encapsulated on the top and bottom by a horizon. After you realize that on a MODFLOW-based structured grid, you'll see the 3D representation is in the top right here, where you have the corresponding cell representation. And then if you look at the layer views in the bottom right here, you can see the cell edges. And likewise, in the row and column view, you can see the cell faces or the cell edge in different perspectives. So it's very flexible in terms of the 3D visualization of both the conceptual and the numerical representation. The other nice addition in this release is that now we calculate and display the water table after you've done a standard MODFLOW 2000, 2005 run. The water table is stored as a surface data object, which can be displayed in a 2D plan or a 3D view. When you're looking at the water table in a cross-section, it's drawn as a line when you're looking at a row or column view. We have two options for that. It can be drawn as a smooth interpolated line where you have a more gradual change between adjacent cells, which is ideal for a regional or larger scale model. The other option you can choose is to have a discrete water table line, which essentially will draw the water table in each column of cells as a flat line and then connect that to adjacent cells. So that option really more closely honors the true water table value and the MODFLOW cell geometry. The water table data can be exported out to a CSV file. That includes the location of the water table in each layer, the location of the layer where the water table exists, and this can be done for steady state or transient runs. So if you have water table calculated at multiple time steps, that can be exported to a CSV file. So it's a very effective visual presentation and representation, and also with the export allows you to do post-processing with other tools such as Surfer or ArcGIS if you want to reinterpolate and adjust the contouring routines outside of MODFLEX. The other improvement we've made is with coloring of both model objects and also property zone objects. The first, let me talk about these user-defined color classes. So when you're looking at connectivities or initial heads or calculated results such as heads, drawdown, or concentration, and also now the water table, previously you were limited in what you could do in terms of the changing the color classifications for the rendering for both the color shading or the stretch view of the results. Now what you can do is you can define your own color class values and the number of classes that you want to see. And so you can manually enter that to correspond to, for example, logarithmic values, or if you're looking at concentrations and you want to have those rounded off to local guidelines such as 10 milligrams per liter or 100 or 1,000 milligrams per liter, that's now possible. So the values you put in there will then be reflected in the 2D and 3D visualization, and you can see here, hopefully, it's also going to be reflected in the legend that's displayed in the 2D and the 3D views. So really this gives you greater control over the 2D and 3D presentation of your model inputs and your results, allowing you to customize it to your own specific requirements, and should give you overall experience when you're doing your presentations. The other change we've made in this release is we've improved the way properties, recharge, and evapotranspiration zone IDs are colored. So what we've adopted is the default color scheme that's used in VMOD Classic. You'll see the screen on the right shows a comparison of the properties, their hydraulic conductivity colored by the zone ID in VMOD Classic in the top right, and then the corresponding model when we've imported that into MODFLEX in the bottom right. Really, now we have a kind of a random color palette that's used. In the previous version, the color palette was similar to what you would see when you're rendering an attribute, and sometimes would make it confusing in order to distinguish between if you're looking at the zone IDs or the attribute rendering. The other frustrating thing is that as you add new zones, then the previous zones will get reclassified with different colors. So it was a bit of a nuisance and an inconvenience, so this is now been remedied with this new release. It makes it easier to compare models from VMOD Classic in MODFLEX if you've imported those. And really with the coloration, it's familiar for most of you that have also been working with VMOD Classic for a number of years. As mentioned, this applies to all the properties, recharge, evapotranspiration zones. This is really for all the models. So for structured MODFLOW, MODFLOW LGR, and also for MODFLOW-USG. So with this release, we've added more graphical options in the numerical modeling, but there's still some work to do, and those are some improvements you'll be seeing over the next couple of releases as we identify the key numerical modeling features from VMOD Classic that we need to migrate over into MODFLEX. In the meantime, what we've added with this past release is a way to edit any of the numerical property zone or boundary condition data via a CSV file. So this essentially gives you backdoor access to the input files where you can export out, make changes in the text editor or in Excel, and then import it back in for visualization and processing. Really, this allows you then not to be restricted by the things that are or are not in the GUI at this point, and really gives you freedom to do any type of editing you want to. If you've got some scripts from VMOD Classic or other utilities, you can hook them up to the file formats that we've defined in the manual. It also makes it quite easy if you want to do calibration for your property zones by applying formulas to parameter values. Likewise, for adjusting conductance for river, drain, general head boundaries. This can be done quite easily with this type of format. Other things you can do is you can add and delete cells for existing boundary condition parameters. You can copy boundary conditions to other layers. I know a few people have asked about the ability to deactivate certain boundary condition stresses or wells. Those options aren't available through the GUI quite yet, but you can do so via this CSV editing workflow. And it gives you unlimited possibilities for editing the numerical model data until those options become available through the GUI. And it also allows you to hook up any scripts for more quick or batch edits or updates to the model. This is similar to the approach we took for MODFLOW-USG. For those of you that have worked with that or attended the last webinar, we wanted to get something out there quickly for you to use. So instead of developing a very sophisticated GUI, we just provided a simple means to edit the numerical model inputs via this CSV file format. This is an example of the CSV editing from the Model Explorer. You can right-click on the desired model object. So, for example, for connectivity, you right-click on it from the model tree and then select Edit Attributes. This will create a CSV file, which will load. For most people, it should be in Excel, but if you have this hooked up to another text editor, then you'll see that file loaded in your own text editor. You can then adjust any of the parameters or zones for the specific layer, row, column. And then load the CSV file back in using this reload attributes option. Just go back quickly. One word of warning is that we only do basic validation on the parameters here, so be careful not to enter any erroneous data such as negative connectivity values or alphabetic parameters instead of numeric data when you do this. It really assumes that you're still going to follow the standard rules for these parameters in terms of what values are allowed or not allowed. Other improvements we made in this release is after you've run and visualized, after you run the model and you're looking at the charts, you can now export the chart data to a CSV file. This is for both the flow and transport charts, for the calculated versus observed, and the time series charts. So that allows you to load into your own charting software or right into Excel if you wish, or you can do further chart customizations. We've offered an option when you're creating numerical grids in the numerical workflow to now define the rotation angle for any new numerical grid that you create. Previously, this was only available when you were doing conversion from the conceptual model. And lastly, we've improved the default states and the overall navigation of these workflows. So now, when you've created a workflow and satisfied certain prerequisite steps for other steps later on in the workflow, you can now click directly on those subsequent steps without having to click on the next button 4 or 5 times in a row. So it really makes it much easier to navigate between the different workflow states, especially if you're going from the conceptual to the numerical model and you want to go directly to the translate and run. You don't need to go through looking at the properties, the boundaries, the calibration data each time. Now you can click directly on the translate step and then proceed on to the run. So this has been adjusted for the standard numerical workflow, the MODFLOW-USG workflow, and also the standard conceptual to numerical model workflow. All right, now we'll have a quick look at some of the things we've been working on since the release this past couple months and the plans that we have for next year. The main feature that we've been working on since July would be supporting MODFLOW-SURFACT. This has been one of the most requested features since the MODFLEX was released almost 2 years ago, so we're really surprised at how many people have adopted MODFLOW-SURFACT for not only mining models, but a whole variety of applications. So this seems to be one of the key missing features from Flex at this point. So we're working on adding support for SURFACT version 4. This includes the recharge seepage face boundary, the PCG5 solver, and the fracture well 5 package. We'll also have support for transport packages and processes, which is something that a number of people have asked for, going back to the very early days when we had MODFLOW-SURFACT and VMod Classic. So this will be a nice addition. And we'll also include support for the TMP package, which stands for Time Varying Material Properties, which has a number of applications in mining, but also in degassing applications. So the beta version with SURFACT should be available in the next couple months. I'm hoping early December at this point. We're also going to continue to improve the numerical modeling experience with a number of features that are currently in Classic. We'll move those into VMODFLEX. This includes the ability to do single cell editing for properties and boundaries, so assigning a single zone or boundary condition parameter to a single cell or editing a single cell. Also improving the options for creating and editing pumping wells in the numerical workflow. So for example, clicking on a single well and creating a well at that mouse click location without having to always import well data from an Excel or a text file. So with those additional options and with SURFACT, our plan at this point is to have that release available by March of next year. The next priority and focus will be on the following. These things are based on the number of feedbacks we've received from people that have been using Flex and also previous surveys that we sent out and prioritize accordingly. So we'll start working on the Streamflow routing package or SFR2 package. At first, we'll provide the capabilities that are similar to the STR package in VMod Classic. There's a wide variety of options and capabilities with the SFR2 package. It's a much more complicated and advanced package than the other standard boundary conditions. So your feedback on the options that you most commonly use for streams would certainly help us guide and prioritize those things accordingly. So there are a number of different options for defining how the stream stage is calculated. For example, you can have transient geometry for streams. Again, any comments you have on things you'd like to see most importantly there would certainly be helpful. Next, we'll be working on MODFLOW NWT, which really is just adding support for the UPW package and the ChIMD solver. We'll be adding support for RT3D. We'll continue improving some of the numerical modeling features with some of those aspects that are in Classic but not yet in VMODFLEX. And then also, if time permits, I hope to also squeeze in support for CWAT version 4 before the end of the year. So that release we're targeting to have available roughly this time next year, so around October or early November. So at this point, I'm going to conduct a short poll. If you don't mind participating in this, it'll only take about a minute or so. It's just 2 short questions. You'll see on the right side of your meeting center, a small poll window will appear. If you don't mind giving some feedback, just 2 short questions asking what interface you're currently using for your modeling projects, if it's the new Flex interface or the Classic interface, and general open-ended question, what features you'd like to see added in the Flex interface in the next couple of releases if it doesn't align with some of the things that we've mentioned in the previous slides. So I'll give you about a minute or so to have a look at this and then fill in your answers, then we'll continue on. So just a reminder, if you haven't seen the poll already, it should be on the right side of your WebEx meeting center, as shown on the slide here. Just click on the desired option that you see from there. If you can write any comments if you wish. If it's not working due to technical reasons or you want to have an opportunity to think about it or provide some feedback, feel free to email me at the end of the webinar session, and I'll collect your feedback at that point. My email address is shown on the screen there. So the poll will be closing in 10 seconds, then we'll resume the webinar. All right, thank you for those that took the time to provide your feedback. We'll carry on then. So for the second half of the webinar, for the next 25 minutes roughly, we'll talk about some of the developments that we've been doing to support MODFLOW-USG. So this is the new code that was released a year ago in May with unstructured grids. These are some things that some are still at a prototype stage, or more some methodologies that we've thought about. Others are things that have been done as part of collaborative testing for our development partners. They're not really in our plans for the commercial release at this stage. That certainly can be adjusted based on your feedback or priorities that you see as your projects evolve. So we certainly can do our best to squeeze in some of these unstructured USG capabilities in the releases next year. So the options we'll discuss in the next couple of slides include the quad-based grids, layer-dependent discretization, new version that does particle tracking called MODPATH 3DU, MODFLOW-USG with the LMT package in order to work with MT3DMS, and one feature I didn't mention in the webinar earlier that we won't really discuss, but we are also working on supporting the SAMG solver to work with MODFLOW-USG. So the next couple slides, some of these items for those of you that follow our blog on our website or our LinkedIn group, you may have seen these topics discussed in there. For those that haven't, I'll just recap them briefly, and I'll provide the links for those blog articles at the end of the session so that you can go there and get more details if you're interested. So first thing is what's called the quad-based grids, or abbreviated to Q grids. These are the unstructured grids that include nested, quad tree, octree refined grids. Essentially, a grid cell is divided into four, wherever a specific geometric object intersects that grid cell, whether that be a point, polyline, or a polygon. The benefit of these grids is that the shapes are similar to the rectangular or rectilinear grids of MODFLOW 2005. These grids are smoothed around the refinement region in order to help the solver and accuracy. So the example shown on the screen here is a quad-based grid for the Biscayne aquifer, which is one of the examples that's published in the MODFLOW-USG manual. The grid has been refined around the canals and also around the well fields here. So we've developed a quad-based grid generator in VMOD-Flex. It's similar to the Voronoi grid generator that we have available in the current release. It takes shape objects as inputs to the grid. These grids can consist of any combination of quad tree, octree, and nested grids with various levels of refinement, so there's no restrictions on how many nested grids you have and what level of refinements those can have. The example shown on the screen here, you can see you have the model domain, you have the canals, which is a shapefile, and then the wells, which are a set of points. Each of these features can have a different level of refinement, so you can refine linear features by a certain refinement factor, and each linear feature can also have a different level of refinement. So for example, if you have canals or streams in the middle of the model domain where you want to have more or higher resolution, those can have a higher level of refinement versus constant heads or general head boundaries that are adjacent or along the model perimeter where you're less interested in the level of accuracy there. So those could have, for example, a 1 or 2 level refinement. Same is true for wells. If you have different well fields with different levels, different sets of shapes, those can be refined with a different level. These quad-based grids follow a layer-dependent approach to discretization, which I'll talk about in the next slide. And as I mentioned, it's very flexible. You essentially start with a uniform grid, load in the different shapes. By default, your conceptual model objects, such as your points, polylines, and polygons, are automatically included. And then you build any desired grid customization or refinement that you want. So here's some examples of what the quad-based grid looks like in comparison to the Voronoi grid. For those that may have missed earlier presentations we did on Voronoi grids, these are on the right here, this is the grid geometry that we currently support for MODFLOW-USG and VMOD-FLEX. There's quite a lot of information and details on our website, which you'll find at the end of the webinar session, giving you some more background on what these grid shapes are and what the benefits are. So you can see for the same type of conceptual model where you have a set of wells, with the quad-based grid, essentially what it does is look to see where that point intersects the cell and then divides that cell into 4. And then based on the refinement level you define, it defines it by 4 once more, and then again for once more. The drawback, though, is the well is not always located at the cell center. You can do some trial and error in order to improve that, but really never going to be guaranteed to have that conceptual well object coincide with the cell center. So this is where the ghost node correction can be used to improve that accuracy or improve that offset. So this example here shows a level of refinement of ×3 for that well object. Alternatively, when you're dealing with the Voronoi grid, the well is guaranteed to be located at the grid node, which is the seed for the grid generator, which usually coincides with the geometric cell center. And instead of defining a refinement level, what you define for the Voronoi grid is a target cell size, which is in the form of an edge length. So for example, you say for around these points, I'd like to have a cell size of approximately 50 meters. Again, the other drawback with the Voronoi grid is that the grid generator combines all points, polyline, and polygons into a similar set of refinement levels. You can't customize certain refinements for different linear features. It's similar to what's done with, well, we use the same grid generator triangle that's used in PFlow, where you have different refinement options for points, polylines, and polygons. So in that aspect, the quad-based grids does give you a little bit more flexibility for customizing different levels of refinement around different features. Likewise, if you look at a comparison when you're doing grid generation around river features with the quad-based grid, the cell center is not going to always coincide with the geometry of the original river location, which in this case is represented by a red polyline, which is a shapefile. You can see at some locations, the well location, the cell center is not going to be coinciding with the original river shapefile. Again, the ghost node correction can be used to offset and correct this. Alternatively, with the Voronoi grid on the right here, since the geometry of the river node in the form of vertices and points that intersected along that line, these are seeds for the grid generator. So it means the river feature will more closely match with the cell center. If we compare the quad-based grid to the Voronoi grid for the same shapefile, you can see that with the Voronoi or V grid, it more closely honors the original shape location based on the how that grid generator works. So another new thing we've been working on earlier this year is leveraging the full capabilities of MODFLOW-USG when it comes to the vertical discretization. So just to recap, MODFLOW-USG allows you to have a different level of discretization for each layer. So it has the notion of sublayering. Your model layers do not need to be continuous across the entire model domain, as would be the case for structured MODFLOW models or even FeeFlow mesh, for example. Each layer can have a different level of grid sizing or refinement. This is a figure that's shown on the right here in the MODFLOW-USG manual. It has a number of applications, including defining more higher resolution gridding for surface water features with coarser grid layers as you work your way down. And it's also very ideal for complex geology. So in the case of this simple discontinuous layering shown on the left here, if you have a formation which pinches out down to 0 thickness, you don't need to maintain the minimum layer thickness across the entire model domain. So that layer can actually stop at that location, and the layers above can have a different level of discretization. So we didn't, when it comes to how we handle this in Voronoi grids, it wasn't truly exploited in terms of what MODFLOW-USG offers. So with these new quad-based grids, we've really leveraged the full capabilities of the code in order to provide a much more efficient gridding capabilities to handle both boundary condition modeling and more advanced complex geological modeling. So I alluded to this previously. So what you can do with this layer-dependent discretization, a simple example is shown here. So if you have a multi-layer model, in this case it's a 3-layer model, let's say you have any linear boundary condition in the upper layers such as rivers, but the same could be true for streams or drains. You can have a very high-resolution quad-based grid refinement around layer 1. As you smooth that layer and work your way down to layer 2, you'll see you can have less level refinement below those river boundaries or linear features. And as you work your way down to the 3rd layer, you can see as that grid refinement essentially disappears completely. So previously, with both, like I mentioned, with both MODFLOW and FEFLOW, you'd have to maintain that same level of discretization through all layers, which is very inefficient. Now with MODFLOW-USG and these quad-based grids, we've been able to demonstrate the type of things you can do with the full code, so you really have a better idea and kind of can really appreciate the type of capabilities that you can do with this software. So last slide summarizing the differences between those quad-based grids and the Voronoi grid. This is from a case study that we did that I presented at a conference early in the year. It shows really the different grid geometry for the same type of rivers shown in blue, and there's 3 water supply wells shown in the middle here. And you can see they both have the same level of refinement, so I think it's 50 meters around the river features and 50 meters around the 3 wells. And it really gives you an idea of the type of grids that you can design with MODFLOW-USG. If anyone's interested in these slides from this case study, I can provide this afterwards. The other thing we've then hopefully will be able to unlock with these new quad-based grids will be the ability to bring in an existing MODFLOW 2000 or 2005 model that has a structured grid and convert it to MODFLOW-USG. So many of you may have models such as the example that's shown in the bottom left here, where you have the so-called ugly grid, where you've refined around an area of interest, but those those rows and columns have to extend out across the entire model domain. So we're working on a way to load in those legacy models, create a new quad-based grid, for example, with just a nested grid in the middle, drop off the excess cells. We can reuse the layer elevations, the hydraulic properties, wells. There may be a bit of manual work you need to do to redefine the boundary condition parameters such as the conductances, but hopefully the bulk of the work will be done during this conversion. So this will really allow you to take models, for example, that are not converging right now or take a long time to run with regular MODFLOW, and then exploit the capabilities of MODFLOW-USG with this efficient grid refinement and the other full capabilities that come along with this new code. The other big improvement in the MODFLOW-USG realm would be the addition of MODPATH 3DU code. This is a particle tracking program for MODFLOW-USG. It's developed by SS Papadopoulos and Associates in the US. The main developer is Chris Muffles, and he has a number of co-authors and collaborators that have worked on the code and also done testing the documentation. So they've really done a fantastic job with this program. We've helped out with some of the testing earlier in the year, testing both Voronoi and quad-based grids using 2D and 3D steady state and transient models. And it's a very robust and easy to use program from what I've seen so far. The first version was released in August. The program is based on MODPATH version 6. It includes 2 algorithms, the SSPA method for unstructured grids, and also the Pollock method. As mentioned, we're really just at a testing stage for this at this point. It's hopefully something we can integrate into BModFlex next year, because it would be a nice addition to have particle tracking available for MODFLOW-USG. In the meantime, the program is available for free through the SSPA website. The website is shown on the screen here. You need to just go there, and then look for MODPATH 3DU. Chris, the developer, just asked that you register and then provide a username and email address, and you can get access to the program and the documentation for free. And as mentioned, we have done some testing on this. If anyone's interested on some basic instructions on how it can work with VMod Flex, and please email me afterwards, and I can send you some brief tutorial that we've been working on. Here are some examples we've done with MODPATH 3DU and MODFLOW-USG. Again, as mentioned, we've tested with the Voronoi grids and the quad-based grids with 2D and 3D examples. All these pictures and different descriptions available are on our website on the blog, and I'll provide the website for that at the end of the webinar session. So the last thing I want to talk about for the webinar today is more of a prototype that we're working on that will allow MODFLOW-USG to work with MT3DMS. Most of you are probably aware of the fact that there is no transport processes or packages currently available for MODFLOW-USG other than the advanced version that Saurabh Pandey has been working on, which I believe might be supported in Groundwater Vistas. Aside from that, there's nothing that's fully supported or available and documented and tested through the USGS. So we've had a number of people ask us about transport supported in MODFLOW-USG, and we weren't really able to give a clear answer on that. So we've gone ahead and tried some different things to really make it accommodate or work with existing transport codes that everyone's familiar with. So first, some background on the traditional approach to transport modeling, which for those of you who have done this are probably aware of some of the drawbacks. You have to refine the grid around the area of interest. This is with the standard MODFLOW. Likewise, you have to refine the vertical layering. Outside the area of interest, you need to mark the cells that are inactive for transport unless you want to have really unnecessary long run times. There's a lot of drawbacks and inefficiencies with this approach. The main thing is the gridding. You have extra rows, columns, similar to what I showed before, that span all the way across the model domain. The key difference is there, though, is the number of layers that you have to add. So with the transport models, it often requires you to have much finer vertical discretization than what your flow model has. So that really can significantly increase the cell count, and then also increases the overall runtime. Often you've developed your flow model with a specific grid, but then when you move to the transport model, as I mentioned, you need to refine the grid. This can often lead to some rework that you need to do with the flow model in order to accommodate the new grid structure. So for example, some of the boundary parameters such as your heads or stages may be shifted to different layers. You may get the models no longer converging due to steep changes in grid geometry, what have you. There's a number of things that need to be adjusted after this process takes place. And then lastly, sometimes the decision of where to assign these inactive for transport cells can be an iterative process. It's usually done after an initial run, then you go back, assign those cells by looking at the overall plume length, identifying your receptors and your area of interest, and then rerunning the model, which isn't quite ideal. If the transport model run can sometimes take a day or two, which we've seen with more complex and advanced models. So the approach that we're looking at doing, which as I mentioned is really just a prototype at this point. We have a simple model that's running, but we're really looking for your feedback to see if this is something that would be worthwhile further developing in order to really give some transport capabilities to those of you that are using MODFLOW-USG right now. So really the methodology will be as follows. It'll allow you, you first would design your flow model using these quad-based unstructured grids that I showed earlier. You can fully leverage those capabilities where you can do refinement around linear features. You see some refinement around wells down in the bottom left here using that quad-based grid refinement. You can do refinement around the model edges. There's really no limits for the flow model or the grid structure other than that you have to use the quad-based grid structure. You then would create a nested grid or a submodel which covers the region where you want to run a transport model, similar to a local or child grid for MODFLOW-LGR. A few guidelines here. This grid geometry for the nested grid must be uniform rectangular grid geometry. The size of that must match the smallest cell size of any boundary that goes into that nested grid. So let's say you have some river that spans through that model domain, or some wells where you've done some refinement. The cell size of the nested grid must be a uniform cell size that matches that smallest grid cell in the from the linear feature refinement. The big plus here is that this sublayer can, this nested grid or submodel can include sublayering. So you can have this this nested grid have much more vertical refinement than your background flow model, which is really key for transport, as I mentioned in the previous slide. You need to apply smoothing from the nested grid to the corresponding regional grid, so you have a gradual transition from those cell sizes. Generally follow 2-to-1 rule, which basically says that any specific cell should not have more than 2 neighboring cells along a specific edge. If it does, then that cell will get refined by 4 in order to accommodate that. And the smoothing here should be done both horizontally and vertically. And then lastly, after we do a number of runs and testing, we may look at adding support for the GNC or the ghost node correction package in order to offset any errors that may occur here. So the methodology, or the scientific technical methodology, is as follows. You run MODFLOW-USG for your entire flow domain. Then you run MODFLOW-USG on the submodel grid region, which is highlighted with this blue rectangle here shown on the screen. For the second model run, it'll calculate the heads at the interface between the nested grid and the unstructured grid. These calculated heads are then assigned to the perimeter of the submodel as time-varying constant heads. This is similar to the boundary flow and head package, which is available for MODFLOW-LGR, for those of you that have used that. We then rerun MODFLOW-USG once more in order to calculate the FLO file for the submodel, which is the key input for the MT3D or other transport-based models that use the MT3D framework. And this is done using a modified version of MODFLOW-USG, which uses the modified LMT package. Then the MODFLOW 2005 or MT3DMS base model is created and is run on the subgrid using these new boundary conditions along the perimeter. I should mention it also will utilize any of the other boundary conditions that you defined in the middle of the model domain, such as rivers or wells that are naturally occurring. You can then assign your sink sources to the submodel. What we do is we assign undefined or -1 value to the boundary conditions along the perimeter of the submodel. This will allow for ambient concentrations to flow through those boundary conditions along the perimeter. Then lastly, MT3DMS is run using the flow file and calculates the concentrations only in that submodel region. So you get something essentially that's shown here. So what we'll do is, if we decide to further develop this and provide it through the software, all these will be automated. You don't need to run any utilities by hand or whatnot. You'd essentially build your unstructured grid, define the nested grid where you want your transport model to be run, and all these steps 1 through 7 or 8 will be done for you automatically. It'll create the corresponding boundaries along the interface. It'll extract out the FLO file. It'll create a MODFLOW-based structured grid model in the background. You just run MT3DMS with whatever settings you want, and then interpret the results. So this gives you an idea of what could be possible. If you look at the nested grid in a cross-section view, you can see you can have much higher vertical resolution in the region where you want to run transport, which is key. Alternatively, the regional flow model just has 1 layer. So again, this is possible with unstructured grids. You can have different discretization. Note that in this illustration here, we haven't done any smoothing, as I mentioned previously, but you would need to have a gradual transition from this nested grid to the adjacent cells in the flow model, following that 2-to-1 rule. This would be both smoothing in the horizontal and the vertical direction. So some pros and cons of this approach, just some ideas that bounce around different people that have given some ideas. First, probably the biggest one is that we stick with the MT3DMS familiarity. Anyone that's done transport with MODFLOW-based models will be familiar with MT3D and all the other codes, so it should reduce the learning curve. You have the ability to offer efficient vertical gridding. This gives you a higher accuracy in the region where you want to run transport, which is key, and also minimize numerical dispersion for the transport calculations. You can benefit from the efficient USG gridding, which is available with those quad-based grids that we showed you. Another thing is that any of the codes that are based on the MT3D framework would work in a similar fashion, specifically RT3D and PHG3D, which would both take the FLO file as an input for their calculations. CWAT likely would not work the same way since it is coupled MODFLOW and MT3DMS, so I don't believe that would work with this approach as shown here. This really offers a logical progression for anyone that has an existing MODFLOW 2005 or MT3D model where they've done the big ugly grid that spans through the entire model domain and you have a lot of layers. It may take a long time to run, and it really gives you a way to take those models, bring them into VMOD-Flex and convert them to a more efficient and robust grid, and also stick with the familiar rectangular grid geometry. This approach will be ideal when you want to model transport in a subset of the flow model. Some of the drawbacks is that there's no transport across from the nested grid region to the background grid, so you can't, once you reach that nested grid interface, the transport calculations stop there. They don't continue to go into the background grid. The size of the nested grid is likely a guess. You don't know up front how far that plume is going to migrate. Fortunately, this can be alleviated in VMOD-Flex since we have the conceptual model approach. This allows you to go back and generate a new unstructured grid with perhaps a smaller or bigger nested grid that covers a larger or smaller region. You can then rerun the conversion to the numerical model and this workflow very quickly in order to generate a new set of model inputs. So it's one way to circumvent that drawback there. We're limited to uniform rectangular grid geometry for the transport model since this is a requirement of the MT3D. So those Q grids must be used. This approach wouldn't work with the Voronoi grid geometry. It wouldn't be ideal if you want to run transport across the entire flow model regime. In that case, you're better off sticking with standard MODFLOW. And really, this is just a temporary solution that we're providing. Likely, once something becomes fully supported by the USGS or by MT3D, then it'll likely supersede this. But since we really have no control over how quickly those developments go, we figure we might offer something as a temporary solution in order to allow people to run some means of transport until that's available. All right, so that brings us to the end of the webinar. I've mentioned some different articles and blog posts earlier on. If you haven't been to our website lately, there's quite a few articles on MODFLOW-USG and some of the topics that I mentioned earlier, including the quad-based grid, the MODPATH 3DU example. These are all available from the MODFLOW-USG resources page. And also, if you're still new to MODFLOW-USG and haven't had a chance to look or understand what it's all about and how it differs from previous versions of MODFLOW, we have several articles there to describe the differences, some terminology and definitions of what Voronoi grids are, etc. In addition, we have the blog on our website that describes some of those other topics I mentioned today, including the MODPATH 3DU examples. I have a case study that I did presented at the NGWA Summit early in the year that compares quad-based grids to Voronoi grids and also includes several examples for the CLN wells. Those slides are available upon request. If you're interested, just email me afterwards and I can send those to you. And that will eventually make it onto our website as a blog post as well. As mentioned, we'll record this session and it'll be available on the blog on our website within the next couple days. So that brings us to nearly the end of the hour and the end of the session. If you have any questions at this time, feel free to use the chat option. If something comes to mind afterwards, you can always email our sales group or myself. My email address is shown on the screen there. And there's always a lot more information available on our website shown here. So thank you for your time. And if there's any questions at this time, I can field those.